Hello everyone, so today we'll be talking about titrations in terms of acid-base chemistry. So just imagine that you have a solution, and in that solution, let's say you have benzene, let's say you have toluene, and let's say you have phenol. And you want to know exactly how much phenol is in there. You can use a base, like hydroxide, to react with this acid, and then you can stoichiometrically figure out exactly how much of that phenol is in there, because toluene is not acidic and neither is benzene. So you can use a base, let's use hydroxide, and a burette. And this hydroxide is of a known concentration. I'm just going to put X for some arbitrary known concentration. You precisely weigh out the hydroxide, you put it in a volumetric flask, you dilute it to a certain volume, and you precisely know how much hydroxide is in that solution. And so you begin to drop the hydroxide into the solution. And that will perfectly react with the phenol. And in order to know exactly how much of this is in that solution, you can put what we call an indicator. And an indicator, it changes color at a certain pH. So let's say at a pH of 5, at a pH of 6, it's colorless. But at a pH of 7, it goes from, let's say, clear to pink or to blue or to red or to some other noticeable color. At that certain pH, that indicator will be activated. And so you will know precisely when you've perfectly neutralized the phenol with the amount of hydroxide. And since it's stoichiometric 1-to-1, you'll know exactly how much of that phenol is in there because it's a 1-to-1 ratio. The amount of hydroxide you put is equal to the amount of phenol in the solution. So things aren't so easy. Just imagine that you have a something that's called more than one proton, polyprotic. Let's say you have H2SO4, where there's two acidic hydrogens. And just for arbitrary numbers, just for learning purposes, let's say that this acid has a pK. This acid has a pKa of 5, and this acid has a pKa of 8. These aren't actual numbers, but it's just arbitrary numbers, but the concept is the same. This has a lower pKa, it's more acidic than that. This has a higher pKa, it's less acidic than that. And so just imagine that you have a solution of that, and you want to know exactly how much H2SO4 is in that solution. But if you have something like just let's just call it indicator 1, that becomes colorful at a certain pH, it's not going to necessarily tell you how much H2SO4 is in there, because there's another acidic component in there that this doesn't change, that has a different pH, and thus this won't change color anymore. So you could have a different indicator, let's call it I2, that changes color at the certain pH of when this hydroxide is fully removed, of when this H is fully removed. And so when you look at it graphically for a simple acid, this is the pH, arbitrary numbers, 2, 6, 8, 12. And then this is the amount of volume of titrant, and that means the amount of hydroxide being poured. The solution, let's say, has a pH of 2. And as you start adding base, it's going to become more basic, and so the pH will rise. And let's say you have some device that can monitor the pH level. You'll notice that it'll hit a point where it plateaus. And so this flat landmark, that's a question mark. What exactly does that flat landmark mean? So this flat landmark is the point where the base is in equal concentrations where the acid, is in equal concentrations to the conjugate base. And at this point, the pH is equal to the pKa, and the pKa is the acidity of that acid. And when you keep going, you'll realize that it keeps going up, and then it plateaus again, or it'll just keep going up. And at this point, the midpoint between when the titration ends and to where this pH is equal to pKa point happened, that point in the middle is known as the equivalence point, meaning where it's perfectly neutralized. And this is just for a basic acid. Just a simple acid with one acidic proton. But let's imagine that we have an acid with more than one proton. How would that look graphically? Volume of titrant and pH. 2, 4, 6, 8. Whoops, 2, 4, 6, 8. And so you keep titrating, and just imagine you have some device like a pH meter, and then it plateaus. There's another acidic hydrogen, so it keeps going up, and then it plateaus again. And then it keeps going up. So now we have two of these flat regions. So what is that telling you? That is telling you that the first acidic proton, as you're adding base, is becoming more basic because you're increasing the basicity with using a base. And then it hits that point where pH is equal to pKa, where the conjugate acid is equal to the conjugate base. And then you keep going, and then you hit a magic point here called the equivalence point. It's perfectly neutralized, but that's just the first hydrogen. Now you got to keep going because there's a second hydrogen to neutralize, and it keeps going again. The process repeats, and you also hit a plateau where now that second deprotonated form is in equal concentrations with its acidic form. And so you keep going again, and then you'll realize that there's another equivalence point where it's perfectly neutralized. So you could have an indicator here that a certain pH at pH 6 will change color. You can have another indicator here that at pH, let's call this 10, will change color. And so that color change will show you exactly when you've perfectly, when you've stoichiometrically have neutralized that acid, and because you know the concentration of the OH, you know exactly how much acid you put, how much base you put in there, you know exactly how much acid is in there. And that's how you find analytically concentrations of certain acids using acid-base chemistry. Thank you.